Hi there, my name is Jan. I'm a field application scientist at Redshift Bio, where we've recently launched our second generation instrument called Apollo. This instrument is based on microfluidic modulation spectroscopy, or MMS, which provides high-resolution spectra for extracting protein secondary structure information with previously inaccessible sensitivity. Today, I would like to highlight an EndNote that we've just published with the title Protein Dilution and Subsequent Concentration Provide a Well-Matched Sample Buffer Pair for High-Resolution MMS. But first, please let me give you a brief introduction on why protein secondary structure matters. Above all, structure relates to the protein's activity. In order to function well, the protein needs to be in its proper structural configuration. Smallest deviations from this optimum can already, for example, close binding pockets or remove catalytic sites from their designated position, which may lead to a loss in activity or cause unwanted side effects. Further, structural change is likely to destabilize the protein, which can also result in aggregation. Finally, protein secondary structure provides assessment of similarity and reproducibility, which serve as useful reporter in formulation, manufacturing, and quality control for protein-based products. For accessing secondary structure information, we employ a novel type of transmission IR technology called MMS. This technique allows us to study proteins in their designated buffer environment. Spectroscopically, MMS covers the so-called amide 1 region, which essentially probes vibrations of carbonyl groups. Luckily, all protein backbones contain carbonyl groups, which makes MMS not only non-invasive, but also label-free method. The benefit of looking at the amide 1 band is its sensitivity towards torsion of the protein backbone, as well as the H bonding environment of the individual carbonyls, which gives us a direct measure of both intra- and intermolecular changes. When it comes to IR spectroscopy of proteins, the sensitivity of the technique critically depends on the success of the background correction. In general, spectra of proteins are extracted by measuring the IR absorption of the protein in its buffer solution first. After that, the sample cell is typically replaced by a second cell, which only contains the sample buffer as a reference. Roughly speaking, the raw protein spectrum can be obtained by subtracting the buffer spectrum from the sample spectrum. Performing this referencing accurately is a big obstacle in common IR-based techniques. So one of the great advancements in our MMS technology was to tackle this problem. Instead of using different cells for sample and reference, we use a microfluidic flow system with two entry channels, allowing us to modulate between sample and reference along every spectral sweep. This way of auto-referencing provides a spectral reproducibility of more than 98%, which means that we can detect in principle structural changes of less than 2%. In order to reach a sensitivity this high, the sample buffer and reference buffer must be carefully matched. A great example for how a buffer mismatch may affect protein spectra is presented in this figure. In orange, you can see a typical amide 1 spectrum of hen egg white, lysozyme, and PBS. The same sample was then again measured against a buffer with slightly different phosphate and salt concentration, presented here in green. As a result, the spectrum is completely skewed from the original one, making it impossible to extract any higher order structure information from it. While buffer matching is so critically important, there might be cases where you would only have a sample and the buffer is unknown or not available. For those cases, I'm going to present a dilution reconcentration protocol that generates a well-matched sample buffer pair without moving too far away from the original recipe. In this protocol, we start with the original sample that contains the protein of interest. Here we used lysozyme in its designated buffer, for which we used PBS in this case. Let's say we wouldn't know what the exact buffer recipe was, and or the components were not available. What we can do then is diluting the sample by 50% with a diluting agent that works well with your product. Here, we just used water as an example. In the third step, we can reconcentrate that sample, for example, by centrifuging in a Pierce concentrator, which will generate concentrate and a filtrate. The protein concentrate and the filtrate will then have the same buffer constituents and form a matched pair of sample buffer and reference buffer. In order to prove that, we ran MMS measurements on that concentrate against its filtrate and compared that to the original 50% dilute as a control. For the control measurement, we used a 50-50 mixture of PBS and water as reference buffer. The absolute spectrum generated from this control measurement is presented here in red. The spectrum recorded from the concentrate filtrate pair we overlaid here in blue. Employing area of overlap analysis for these two spectra showed great similarity of 98.2%, indicating that this protocol successfully generated a buffer-matched sample reference pair. The higher order structure analysis extracted from those spectra provides us with a relative abundance of structural motifs. As expected, lysozyme is dominated by alpha helical structure with less of beta sheet and turn components, and lowest abundance of unordered structure. A comparison between the concentrate and the original protein sample reveals that also the protein secondary structure is unaffected by this protocol, as the relative abundance of structural motifs stayed the same. In summary, we have learned that good buffer matching is crucial for the success of any IR spectroscopic investigation of biomolecules. MMS measurements have demonstrated that the higher order structure of lysozyme is retained by over 98% along the dilution reconcentration protocol. Therefore, this procedure can be used to generate a well-matched sample buffer pair if there is no reference buffer available or the buffer recipe is unknown. For more content on MMS, the Apollo, and protein analysis, please consider having a look at our website and stay tuned for our upcoming posts on LinkedIn and YouTube. Thank you for your attention.